Hello everyone and welcome to a new lecture. In this video we're going to talk about slant asymptotes. So in the previous lectures we talked about vertical and horizontal asymptotes, and in the bigger picture we were interested in how the behavior of the graph was doing as x, for example, was approaching infinity or negative infinity, or as y was approaching negative infinity or positive infinity. So in the case of a vertical asymptote, okay, we had at a point at x equaling to a value, we had a line. Okay, that was the vertical asymptote. And we saw how the graph of the function, okay, or how the function, as the x of the functions were getting closer and closer to the vertical asymptote, the y values were getting or going toward positive or negative infinity. So as you have the values of the y's of your function going toward positive or negative infinity, you see your x values getting closer and closer to the value of the x that you have the line crossing the x-axis. Okay, that was a vertical asymptote. And in the case of vertical asymptotes, we were strict. We could not have the graph crossing the vertical asymptote. However, for a horizontal asymptote, we could have the horizontal asymptote, or we could have the graph cross the horizontal asymptote. But eventually, we saw how the graph was getting closer and closer to the horizontal asymptote, meaning the distance between the graph and the horizontal asymptote was going towards 0 as x was going toward positive or negative infinity. So that was about horizontal and vertical asymptote. So if a vertical asymptote looks like this and a horizontal asymptote looks like this, then what does a slant asymptote look like? Well, basically a slant asymptote is at an angle, okay, a combination of those two asymptotes. They can be like that, they can be like that, or they can be like that. Those are examples of slant asymptotes. Slant asymptotes are sometimes called oblique asymptotes, okay? And slant asymptotes or oblique asymptotes can also have the function to cross them, okay? So they are not strict as vertical asymptotes. However, as we go toward infinity or negative infinity, we see the graph of the function getting closer and closer to the slant asymptote, okay? So when do we have a slant asymptote? Well, we have a slant asymptote, so if we have a rational function r of x equaling to p of x over q of x, if we have a rational function like that, such that the degree of the numerator is n and the degree of the denominator is 1 less than the degree of the numerator, so it is n minus 1. So only in that case we have a slant asymptote. So if the degree of the numerator is 3 and the degree of the denominator is 2, we have a slant asymptote. If the degree of the numerator is 100 and the degree of the denominator is 99, then we have a slant asymptote. So only when we have the degree of the numerator to be 1 more than the degree of the denominator, then only we have a slant asymptote. So for example, a rational function like x to the 2 over x minus 5, then in this case we have a slant asymptote. If we have x to the 500 minus 3x to the 2 plus 5 over x to the 499, then again we have a slant asymptote. Okay, so only when we have the degree of the numerator being 1 more than the degree of the denominator, then we have a slant asymptote. Okay, so how can we find slant asymptote, or what is the equation of a slant asymptote? Well, when we divide p of x by q of x, so r of x equals to, so always we have a quotient. Okay, so suppose the quotient is a, okay, or let's denote it with a capital A. The quotient is a, okay, then a added to the remainder, so r is the remainder, over the divisor, which is q of x in this case. Then this a right here, this is the equation of the slant asymptote. Okay, so when you divide p of x by q of x, so this is equal to p of x over q of x. This p of x is the dividend, the q of x is the divisor, it divides p of x. Then when you divide p of x by q of x, you always have a quotient. Suppose the quotient equals to a, you have a remainder, and you have a divisor. Okay, so this a right here, which is the quotient, this is the equation of the slant asymptote. So let me give you an example. So example 1, let's have this in front of us like that. So example 1. Suppose I have minus 4x minus 5 over x minus 3. As you can see, we have a rational function. Okay, we have the degree of the numerator to be 1 more than the degree of the denominator. Then we do have a, yes, we do have a slant asymptote. And we find the slant asymptote if we find the quotient of this division. Okay, so let's do the division right here. So we have x to the 2 minus 4x minus 5 being divided by x minus 3. X minus 3 is the divisor. So x to the 2 divided by x, we have x right here. So x times x is x to the 2 minus 3x. Okay, so if we subtract this, so x to the 2 minus x to the 2 is 0. Minus 4x plus 3x is minus 1x, or just minus x. Okay, so we'll bring this minus 5 down. So minus x divided by x is minus 1. 1 or minus 1 times x is minus x, and plus 3. Okay, so we're gonna subtract those two. This will be positive, this will be negative. So we will have 0 and then minus 8. So minus 8 is the remainder, x minus 1 is the quotient, and x minus 3 is the divisor. So x to the 2 minus 4x minus 5 over x minus 3 basically equals to the quotient, which is x minus 1, okay, plus the remainder, which is minus 8 over x minus 3. So this right here, this is the equation of the slant asymptote. Okay, so if the equation of y equaling to x is like that, sorry, it's like that. This is y equaling to x. So what is y equaling to x minus 1? Well, we will go to the right by 1 degree. So it is like that. This is the equation of y equaling to x minus 1, and this is the slant asymptote. Okay, that is basically how we find the equation, or that's how we find slant asymptotes. When we have a polynomial such that the degree of the numerator is 1 more than the degree of the denominator, then when we do the division and we find the quotient will be the equation of the slant asymptote. Okay, so let me give you another example. So example 2. So example 2. Suppose I have x to the 2 minus 6x plus 7 over x minus 5. Actually, plus 5. Okay, so since we have the degree of the numerator being 1 more than the degree of the denominator, we do have a slant asymptote. Okay, all we have to do is to find the quotient when we do the division, and that will be the equation of the slant asymptote. Okay, so let's do the division. X to the 2 minus 6x plus 7 being divided by x plus 5. So x to the 2 divided by x is just x. X times x is x to the 2 plus 5x. Okay, so if we do this subtraction, we will have 0 right here, and then we have minus 11x. We will bring this 7 down. So minus 11x divided by x is just minus 11. Minus 11 times x is minus 11x minus 55. We will have 0 right here, and then minus 55 added to 5 is plus 62. Okay, so x minus 11 is the quotient, and plus 62 is the remainder. So the equation of the slant asymptote equals to x minus 11. Okay, so that is basically how we can find the slant asymptote of a rational function. So now let's look at what a slant asymptote looks like on Desmos. Okay, so suppose we have this rational function. We have x to the 2 plus 1 over x. This is a rational function. We have a polynomial on top and we have a polynomial on bottom. And as you can see, the degree of the polynomial on top is 1 more than the degree of the polynomial on bottom. Therefore, we have a slant asymptote. We have to find the equation of the slant asymptote, and we will be able to graph it, basically. Okay, so how can we find the equation of the slant asymptote? Well, we can break this addition right here. So we can have x to the 2 over x plus 1 over x. Okay, so x to the 2 over x is just x plus 1 over x. That is the equation. So have it in front of your eyes. X plus 1 over x. So x plus 1 over x, the x that we have, that is the equation of the slant asymptote because that is the quotient. Okay, 1 over x, the 1 is the remainder and the x is the divisor. Okay, so y equaling to x, that is the equation of the slant asymptote. And you can do the division right here. You will get that. So let's do that. Y equaling to x. And let's see if that's the case. So let's put it right here. So as you can see, this is a slant asymptote, y equaling to x. As x goes larger and larger, we have the graph getting closer and closer to the slant asymptote. Okay, if we zoom in, if we grow our x to go toward infinity, for example, or minus infinity, the graph gets closer and closer to the slant asymptote. And that was a definition of a slant asymptote. Okay, so just to remind you, we can have a slant asymptote such that the function crosses the slant asymptote. Okay, so if I deactivate these two and activate these. So this is a slant asymptote. I can change the parameters, so I can change the value of the b and the value of the a, and we will see that the graph actually crosses the slant asymptote. However, in the long run, we have the graph getting closer and closer to the slant asymptote. Okay, let's see. Well, yes, it is getting closer and closer to the slant asymptote. Okay, so that is basically what a slant asymptote is. And with this, we come to the end of this lecture.